Good. So once again, thank goodness for YouTube and that all of these things will still make it onto YouTube. But in our sort of in our introduction here, I was just pointing out the difference between aldehydes and ketones structurally. We've really already gone over these generalized forms of aldehydes and ketones. We also said that the simplest possible aldehyde will be formaldehyde. No one really calls it methanal, although that name isn't wrong, just no one uses it. People will raise their eyebrows at you if you call it that. So that's the smallest possible aldehyde. So it's permissible for there to be two hydrogens on here, but you do need at least one directly attached to the carbonyl in order for it to be an aldehyde. What about ketones? Well, these two groups, R1 and R2, can be the same or different, and we'll look at examples of both. We'll practice naming these things in a short while. But we do require that these two groups be alkyl groups. They cannot be hydrogens for, I think, obvious reasons. If either of those R groups is a hydrogen, you don't have a ketone, you've got an aldehyde. So the smallest possible ketone is acetone, which has 3 carbons. You need at least 3 carbons to make a ketone. Try it, you'll see you won't be able to make a 2-carbon ketone. So just any more than you can have a 2-membered ring. Good, so I think that's all we really need to say about that. Again, I'll repeat, ketones and aldehydes have very similar reactivity. I would say the main difference between the two is, other things being equal, aldehydes tend to react a little bit faster than ketones, but they have very much the same reactivity. And we'll learn in this chapter some of the reactions that aldehydes and ketones undergo. At least I think those that will be most helpful for us to understand carbohydrates in chapter 16, which is where we're going to go next after chapter 9. So what might be some examples of naming these things? Well, again, aldehydes in the IUPAC nomenclature, not to mention, of course, you'll get to practice this in OWL, but we can do a few here. But the IUPAC ending for aldehydes is AL, AL, and the IUPAC ending for ketones is ONE, O-N-E. No big surprise, I'm sure. But other than that, the rules and building blocks for naming are just like naming alcohols or alkanes even. So, you know, what if we had 4, 5, 6, 7, 8. I'll even also get you guys used to this. If you ever see CHO, it's an abbreviation for an aldehyde group. And so the reason we write CHO instead of COH is because OH sounds like an alcohol. So in order to be less confusing, we use CHO. But this means C double bond O H. It's just an abbreviation for an aldehyde group. So I don't know, let's do this. And I hope I counted 8, 4, 5, 6, 7, 8. So there's 8 carbons in the chain. So that's going to be named as an octanal. And you don't have to say 1 octanal. In fact, I wouldn't, because it's unambiguous. The aldehyde carbon has to be on carbon 1. It has to be on the end. Otherwise, you don't have an aldehyde. And then we do want to say that in carbon 2, there's 2 methyl groups, so this will be 2,2-dimethyl octanal. Just like you would name any other functional group. See if I can fit it. There we go, barely fit it. So I think that's the best name for that compound. One other common name besides formaldehyde and acetaldehyde, I think you already know benzaldehyde. That's a benzene ring with an aldehyde group. That one's worth knowing, and I think you would learn that in chapter 4 when we discussed aromatic compounds, benzaldehyde. I've never heard it called anything else. And as I think I also mentioned at the time, I think you're familiar with the smell of formaldehyde from your high school biology classes and dissecting things. And most aldehydes smell really disagreeable like that. They all something like that. One of the major exceptions, the most important exception being, how did I get the 2,2 again? Because the aldehyde is carbon 1 by definition, it has to be. If carbon 1 does not have a carbonyl on it, then it's not an aldehyde. So that's why you don't say 1 octanol. It's understood. So if this is carbon 1, then carbon 2 is 1 over, there's 2 methyl groups on it. And I purposely put 2 on there so I didn't have to worry about stereochemistry. That carbon, there's no chiral carbons now. So I did that to make it easy on myself and on you guys. But back to benzaldehyde, that's just about the only aldehyde that smells really nice. And I couldn't tell you why. Who knows how those funny smell receptors in your noses work? Well, I don't. You might know more about that than I do. But people do differ as to what benzaldehyde smells like. Some people say it smells like almonds. Some people say maraschino cherries. But everyone agrees it smells very pleasant. But that's about the only one. Most aldehydes smell really, really bad. What about ketones? Well, let's see. Where should I put it? Sort of sick of methyls. We'll put it here. Oh, let's put a chlorine here just for fun. No, let's not do that. I take it back. 2, 3, 4. No, I don't take it back. Let's do it. It's not going to be so bad after all. So in this case, we want to number for the ketone. I think it makes the most sense to start here. We could try numbering it the other way also. But I don't think we'll get anything any better. Well, we might. Let's see. Let's change to a different color. You remember this, if you don't know which way to number, try both ways. Well, isn't that interesting? I just feel really weird using the red numbers. It just doesn't feel right to call this 1-chloro-6-heptanone. Seems really weird. I think the ketone would take priority. I think we're best calling that 7-chloro 2-heptanone. And certainly without the chlorine, this would just be plain 2-heptanone. So again, heptane, just like 7 carbons with a 7-carbon alkane, and -one for the ketone ending, and 2 to say where the ketone carbonyl is. So the alternate name would be the red numbers. It'd be 1-chloro-6-heptanone. It just seems weird to me for the chlorine to take priority over the ketone. I think the ketone would take priority since that's what we're naming it as. So I think that's the better name. The other name seems a little weird to me. Ketones can certainly be cyclic. You could have something like this, for sure. That would simply be cyclopentanone. Cyclopentanone. And again, I don't think these names are any surprise at all. So that's the basics of naming aldehydes and ketones. You'll get to practice more of that, as I said, when you work on the OWL assignment, but it's why I always say, after we've learned to name alkanes at the very beginning, honestly, if you know how to name alkanes, you know at least 85 or 90% of what you need to know to name anything. And all we're really adding here is these endings al and -one for aldehydes and ketones. Good. Any other questions on that? Let's see. Oh, right. And I mean, I just want to point out we had a compound like this before. Actually, I think that was even one of the ones you memorized in chapter 4. That one's called acetophenone, methylphenylketone. We already know how to make compounds like that from benzene. Just a reminder, we covered this in chapter 4. What was the name of what the last one we did? Oh, geez. Cyclopentanone? Yes, thank goodness for Control Z. If it weren't for that, I'd be in trouble. Good, so we're already familiar with acetophenone. If you want a reminder, that compound happens to be called acetophenone. No one really calls it phenylmethylketone. But you learned that in chapter 4. If you've forgotten about that, you can go review that table in chapter 4. That has, oh, I don't know, maybe 6 or 8 really common aromatic compounds that it's worth learning their names because you run into them pretty often. But it's a pretty terrible bond, isn't it? But we learned in chapter 4 that you can make aromatic ketones of this type using an acylation, a Friedel-Crafts acylation reaction. So you'll use acetyl chloride in this case, though you could use any other acid chloride you liked, and then either aluminum chloride or iron 3 chloride, doesn't matter which. So that's in 4.9 if you've forgotten that reaction. So the reason I'm mentioning that is we know how to make, in principle, aromatic ketones of this type. And you just swap out this methyl group and you'll have another alkyl group over here. But basically what you need to know is that you swap the chlorine in the, wait a minute, I lied. You swap whatever is attached to the chlorine in the acid chloride with one of the benzene hydrogens. It's a substitution reaction, right? Electrophilic aromatic substitution. And you do get HCl as an inorganic side product. We won't isolate that, of course. We're interested in the major organic product. But if you've forgotten about that reaction, please review it. It's always good to make connections to previous chapters when you can. Good. So what else do I need to cover today? We're at 3:25. We go to 3:45. So that I think is enough in terms of the basics of structure. What about physical properties of ketones and aldehydes? Well, the carbonyl group is pretty polar. It's not the most polar thing there is. I would say carbonyl groups are less polar than your protic groups like alcohols or carboxylic acids, but still pretty polar. Not polar enough to make most ketones and aldehydes water soluble, although the smallest ones are. Formaldehyde's water soluble, for instance. But once you start getting into 4 and 5 carbon aldehydes and ketones, these are not terribly soluble in water any longer. And again, part of that can be because even though both of them have this carbonyl oxygen with its 2 lone pairs on it, this can act only as a hydrogen bond donor. Only as a hydrogen bond acceptor. So there's no hydrogen bond donor abilities in these things. Remember, for hydrogen bonds to be both donated and accepted, you have to have either an OH bond or an NH bond, at least one of those somewhere in the molecule. And we don't have that here. So ketones and aldehydes can accept hydrogen bonds, and you see things like that and similar to that going on in DNA even. The double helix, the so-called rungs of the ladder are hydrogen bonds, and some of the atoms involved in those hydrogen bonds are only hydrogen bond acceptors. They're not hydrogen bond donors. So it does have the ability to accept hydrogen bonds, but not full H bonding ability. So for that reason, these functional groups, ketones and aldehydes, are pretty polar, but nowhere near as polar as like alcohols or carboxylic acids. But certainly more polar than alkanes, with the expected results in terms of, increased boiling point is the main one that we've discussed. Other things being equal, compared to alkanes, let's say, of similar molecular weight. Let's see if we can even do one more. I forget where acetone boils, maybe 60 something or 70. Let's use our Google. H bond acceptor if it's got a carbonyl group. Acceptor only. Acetone boiling point. I saw degrees F. Yeah, 56 Celsius. So let's write that down. And of course, you don't have to memorize this. You see, I don't have it memorized. I actually was a little bit high. I thought it was above 60. So this is C3H6O. That gives us 36, 42, 58. Where's butane? Is that close in molecular weight? That's C4H10, 48, 58. And what did we say this one was? I forgot already. 15, 30, 42, 50. Is it equal? Wow, what a coincidence. So butane, I'm quite confident is, I think it boils above 0, but not by much. I think it's like 15 or something like that. -1, actually. I was off by a little bit. So there you go. This sort of difference in properties is easily explained by not hydrogen bonding in this case, but purely because acetone is so much more polar than butane. So you got dipole-dipole interactions. So all that stuff you learned in Gen Chem about intermolecular forces still matters here somewhat. So that should at least give you an idea. And of course, you don't have to memorize those boiling points. I really thought that butane was more like 10. I thought it was, didn't know it was as low as -1. But anyway, that I think I've made my point there. Good, so as you can see in the class notes, I'm kind of jumping around a little bit in terms of the order that I'm covering the sections. I believe my order makes a little more sense. That's open to discussion, I suppose, or at least in principle, but I thought I'd mention this oxidation business since we covered that pretty recently in chapter 7. Remember where we said that alcohols can be oxidized depending on whether they're primary or secondary, and of course tertiary alcohols cannot be oxidized, no matter what oxidizing agent you treat them with. Well, I just wanted to remind you that aldehydes, since we have a chapter on aldehydes, can be oxidized to the corresponding carboxylic acid, CO2H. And we learned that Jones reagent would do that. PCC is too mild. PCC will not oxidize an aldehyde. Pyridinium chlorochromate, Jones reagent. But we learned about some others here. Actually, even oxygen in the air will do this slowly, leading to some interesting effects. If you were to take a bottle of benzaldehyde or whatever aldehyde you like and leave it open, in the hood, please, in the fume hood, please, after not very long, you'll see this white sandy-like stuff appearing on kind of the top where the top of the bottle screws on. And that is benzoic acid. It's benzaldehyde getting oxidized just by the oxygen in air. And air is only like 20% oxygen, but that's enough, at least over time, to oxidize aldehydes. They will oxidize them to carboxylic acids. But Jones reagent is one. I guess you could say oxygen's another, O2. Other oxidizing agents that work, one of them is silver 1 oxide, Ag2O. It's another pretty good oxidizing agent. Silver is here in the +1 oxidation state. Silver doesn't like being an ion. That's why we make so many things out of it. It would much rather get reduced from silver +1 to silver metal, silver 0. And so as such, this is an oxidizing agent, and that will certainly do the trick. And one other real common oxidizing agent that's not bad for you guys to know about is potassium permanganate. The permanganate ion, MnO4-, is one of the strongest oxidizing agents known to man, and that will certainly have no problem oxidizing an aldehyde to a carboxylic acid. This is manganese. If you work it out, of course, potassium's +1. This is normal -2 oxygen. So 4 of those, did I say -2? Yeah. So 4 -2s makes -8. With the +1 from the potassium, we have -7 to cancel out. That means the manganese is in the +7 oxidation state. That's just about as high an oxidation state as you can get on any metal. So it's a very, very strong oxidizing agent. So that's worth bringing up, I think. I also want to point out, as kind of an aside, ketones cannot be oxidized any more than tertiary alcohols can be oxidized. So you can treat a ketone with whatever of these oxidizing agents you like, it'll just look at it. I think I've said enough there. Yeah, so ketones can't, that's already as highly oxidized as we can get. Good, and in my waning 15 minutes or so, I really just want to make 1 or 2 more points about the carbonyl group in general. And I think that will help us to put into context the reactions of carbonyl groups that we're going to learn about, the reactions that ketones and aldehydes undergo. And one of the things that I want to point, I guess my main next point is going to be that both ketones and aldehydes are good electrophiles, or they're good Lewis acids. I had this idea just on the way to class here. I'm thinking about, except it wouldn't work because they use the words electrophile and nucleophile in the book. But I wonder what it would be like if I simply never used those words, nucleophile and electrophile, and only spoke of Lewis bases and Lewis acids. I don't know if that'd make it any better, but I think it's rather silly that there's these 2 sets of names that mean exactly the same thing. But so both aldehydes and ketones are good electrophiles, good Lewis acids, if you like. They like to accept electrons. And there's a few reasons for that. One reason is that all carbonyl groups, regardless of what kind of compound, all carbonyl groups are resonance stabilized species. There's another resonance form that you can draw that has a minus charge in oxygen and a plus charge in carbon with only 6 electrons around carbon. Of course, that's a minor contributor. Of course, the structure looks much more like this than like this. But even though this is a minor contributor to the overall structure, it's important. It's because of this resonance form, this part of the resonance hybrid, that is at least part of the reason that ketones and aldehydes are such good electrophiles. No wonder, because there's a partial plus charge in this carbon. Normally, we will use this resonance form when we draw aldehydes and ketones. But I think because we know there's a partial plus charge in oxygen, no wonder that we can expect nucleophiles to attack that carbonyl. And that's what we're going to see. We'll learn a few reactions of aldehydes and ketones, a few of the ones that there are, or a few of the ones we could learn. But I'll try to limit it to those that I think will help us out the most, especially when we get to chapter 16 on carbohydrates. So that's part of the reason that these things are such good electrophiles, such good Lewis acids. Another reason, I guess, you can get just by looking at the structure of a generalized aldehyde or ketone by itself and observing that oxygen is quite a bit more electronegative than carbon. That means that this carbon-oxygen bond is polarized heavily towards the oxygen. And so just by virtue of the inductive effect, we find that, that the carbon has a partial plus charge. So both of those explanations are true. This is an explanation involving resonance. And what we're explaining here is why ketones and aldehydes are such good electrophiles. So this is a resonance explanation, and this over here is just an inductive effect explanation. And it's a funny thing. A few years ago, one of my students with a good sense of humor pointed out that it really seemed like an answer to pretty much any question about why this or that happens in organic chemistry that a professor might ask. In answer to pretty much any question, if you guessed resonance or the inductive effect, you'd have a good chance of being right. And here they both contribute to the explanation. So what this means is that whichever way you want to look at it, whether by just the inductive effect of two atoms connected that are very different in electronegativity, with the oxygen being an extremely electronegative atom, that's putting a partial plus charge in the carbon atom, or if you want to look at it as a resonance thing, that shows that there is a minor but still critically important contributor that puts a plus charge in carbon. That's another way of saying there's a partial plus charge in carbon. So ketone and aldehydes are good electrophiles. Yes, that's exactly right. And that means that we can expect to see nucleophiles adding to aldehydes and ketones. And pretty much everything we learn about is going to look like that. We're going to have some aldehyde or ketone. There's going to be some nucleophile or Lewis base, something with an extra electron pair one way or the other. This is extra electron density on it. It's got a partial minus charge, if not even a full minus charge. And this is going to be our electrophile. We got a partial plus charge in this carbon, as we've just established. So completely unsurprisingly, this nucleophile is going to attack that carbon and will, of course, break one of these carbon-oxygen pi bonds. We have to, otherwise the carbon will have 5 bonds, 10 electrons around it. And so you'll then get intermediates that look something like this. And I mean, there are variations on this. There are also reactions in acidic solution where you actually have to protonate the carbonyl oxygen first. I don't know that we're going to get into the nitty-gritty of the mechanisms of those, but basically you're going to expect to see things like this happening. And I think that's exactly what we will see starting on Wednesday. Let's see, what else can I say? Aha. I mean, I still have 8 minutes left. I don't know, yeah, 8 minutes left. I don't know that I'm going to be able to use them all. I also know that not a soul will blame me if I don't. I just want to make sure that I've got at least, I just want to get us all ready to start getting into the actual reactions next time. Let's see. Yes, so trying to think if I have a good way of, I'll just clear everything and draw that again. So this type of reaction, when should we know what you made in the exam? Well, you should know your raw score already. I don't know the average yet. Because there's still some people that need to take it, but the very second I know it, I'll put that on eCampus. Right now, I think it says average yet to be determined. I'll change that as soon as I know what the average raw score is. And I'm hoping that I'm able to figure out the curve and put up curved scores by the weekend. I hope so. I'm hoping that at least you'll be able to come to class on Monday and know what your curved score is. I'll try my best. I just want to be sure that everyone's taken it. Good. Where was I? Oh, so we said that nucleophiles were attacking here. I'm just redrawing what we had a moment ago. And you might call this a nucleophilic addition reaction, nucleophilic acyl addition. There's that word acyl again. And so they generally look something like this. We could call this nucleophilic acyl addition. And we might look at 1 or 2 of the mechanisms of these things. I'm not going to go crazy with mechanisms. I never do. I never want to in this class. Nucleophilic acyl addition. And we'll definitely start in on those on Friday. I keep thinking today's Monday. We'll definitely start in on those on Friday. And then there's another class of reactions of acyl compounds with nucleophiles. That's pretty much going to be the domain of chapter 10. So we'll get there. This class of reactions is for us now in chapter 9. But the difference in chapter 10 is we're going to have some leaving group here. Can I just go LG for leaving group? and we're going to treat this with a nucleophile. And in perhaps multiple steps, I don't think we'll go very crazy with mechanisms there either, if at all. But after adding a nucleophile, that nucleophile is going to substitute for the leaving group. And you can call these nucleophilic acyl substitutions. And we'll get to those later. That's not in this chapter. That'll be in chapter 10. And oh, is that ever going to be relevant when we start talking about polypeptides and proteins and how those things are put together? But I'm hoping that by now, these types of reactions or these names, even if you wouldn't have thought of it ahead of time, I'm hoping at least they are substitution. I'm hoping they're at least very unsurprising. You know, we already know what an addition reaction is. A plus B yields AB, right? And this is just falls into that exact same category. And then we know what substitution reactions look like. They're more like AX plus Y yields AY plus X. So two things are switching places. And we've seen a good number of those this term as well. So that being said, we're going to start in on, I would say, nucleophilic acyl addition reactions next time. And I still am about 3 minutes early, but I don't think anyone is going to blame me. So keep an eye on eCampus. As soon as I hope to know the average by, the raw average by Friday, or certainly at the very least by some time on the weekend. I just want to make sure that everyone's taken the exam before I post that. Right, and then as soon as I know the curved scores, I'll post them too. Oh, and I am aware that the Q drop date it's not real soon. It's not like imminent, but I think it's in about 2 weeks or something. You should certainly know your grade on the exam, and I'll also recalculate estimated class grades by then. So I would think you'll know that well before that decision date. Other than that, I won't say I'm out of time because I'm not, but I think that's a good place to stop. So I'll let you guys off a couple minutes early, and I'll see you all on Friday.